All right, in this video we get a little bit more practice with the signed area concept and look at a couple properties of definite integrals. Okay, so if we focus, for example, on the definite integral that is down here in the lower left corner, notice that this is an integral of the definite integral type, an integral from a to b of some function f of x dx, but that function f of x is the sum, the function x cubed over 3 plus 2x, is actually the sum of two other functions. Let's call them g and h. So the function g of x here that we're seeing is x cubed over 3, and the function h of x is equal to 2x. All right? And so we know that if we were going to find the definite integral of this problem, we could do the fundamental theorem of calculus, which would involve finding the antiderivative at 2 minus the antiderivative at 0. All right, but so that is a possibility. But what we can see over here on the left is the function itself given as the black dotted line. So the black dotted line function is x cubed over 3 plus 2x. And we are interested in the definite integral, finding the area under this curve from 0 to 2. Okay, so from 0 to 2, we know that if you do the fundamental theorem of calculus on this problem, that you are going to get 5 1/3, 5.33 repeating, or 5 1/3, sometimes called 16 over 3. So that's what you're going to get from the fundamental theorem. Okay, but we can see that the antiderivative is x to the 4th over 4 plus x squared. We can see that in the graph, in the demo to the left. And what we're essentially seeing here is that this antiderivative, capital F of x, is made up of two other antiderivatives, g of x and h of x, and you can add the antiderivatives together. So when we see x to the 4th over 12, that is the antiderivative of the function g of x, x cubed over 3. So the antiderivative is x to the 4th over 12 of that part of the function. Then there is h of x, which is the function 2x, and the antiderivative of that function is equal to x squared. And we can find the antiderivatives of those functions separately, and it is those two antiderivatives added together that makes the antiderivative of the function f. Okay, so that is what we're seeing in one of the first properties of the definite integral here, that if you have the definite integral of two functions from a to b of f of x plus g of x, the two functions added to each other, then you can find the antiderivative and then do the definite integrals of each part separately. Okay, so that is the first thing that we're seeing from the property of the definite integral. The next property we're going to look at is focusing on the concept of the signed area itself. So let's add a page below. There is a third property of the definite integral that we'd like to look at, that the definite integral from a to b of some function, f of x dx, okay, in this case our function is the x cubed over 3 plus 2x function, then that definite integral is equal to the definite integral from a up to some new value of c, f of x dx, plus the definite integral from that value c up to the value b, the upper limit of the original integral, f of x dx. Okay, and the meaning of that in this problem, for example, is that this definite integral from 0 to 2 is this integral from a to b. So we're seeing here that a is equal to 0 and b is equal to 2, and the function f of x is equal to x cubed over 3 plus 2x. Right? But according to this property, we can split this integral from 0 to 2 in an integral from 0 up to some new value that we come up with, like 1 for example, and then we integrate the same function, plus the integral, definite integral from 1 up to the original value b, which was equal to 2 f of x dx. So this is what the property, this new property of the definite integral is saying. And I would like to justify it in a geometric fashion. So notice here that we have the first integral, 0 to 1 of f of x dx. In the picture over here, rather than doing the integral from 0 to 2, we're just going to integrate from 0 to 1, some value that is somewhere between 1 and 2. So I will stop at a value of 1. Okay, and we can see that when you compute that integral, you will get 1.0833. And you obtain that from the fundamental theorem of calculus, like you did the original problem to get 16 over 3. We did the fundamental theorem of calculus to get 16 over 3. But to get 16 over 3, we use the limits 0 and 2. Now to get the 1.0833, we're just using the limits of 0 and 1. Okay? And that gives the 0 to 1, which gives an area of 1.0833, is the region shown in the pink triangle kind of there. Okay. And then there is another integral that can be done, the definite integral from 1 to 2, and that will look like the remainder of the area. So there is the region from 1 to 2. And that area comes out to be 4.25. Okay, so what we're seeing in this picture, what we're seeing from this example is that when we do a definite integral from 0 to 2 of the function, we knew that we got 16 over 3, which was 5.33 repeating. Okay, and then that gave us the region. It kind of looked like this, a triangle region. And then we found the area of the whole region here. But then the property of the integral said that that 5.33 was equal to the definite integral from 0 to 1 of f of x dx. Okay, so instead of going from 0 up to 2, that integral is going to be equal to the 0 to 1 integral. Here was that whole region again, but instead we integrated from 0 to 1 and we got only part of the area. And then there was another integral that we could have computed, plus the integral from 1 to 2 of f of x dx. Okay. And again we had that same region, looked like this, but from 1 to 2 we had a different part of the region. And it was these two together, this region here in blue is the region that fit right here at the tip. Okay. And if we put these two regions together, that the whole area, which was 16 over 3, was equal to the area of the little bit at the front, which was 1.08 whatever plus, and then there was the part at the end which had an area of 4.25. Okay, and if we added those two values together, the 1.0833, that leads us to the 5.33 repeating, which was equal to the 16 over 3. Okay, so what we're essentially saying is that these properties of the integral make sense when the function is greater than 0, right? We can interpret the definite integral from a to b of f of x dx. We can interpret that as a positive area. And when we have a positive area, we can agree that the definite integral can be split into smaller areas from a to c, f of x dx, and then you get the remainder of the area from C to the end of the original region B, and here is what we have in terms of area 1, and then you have another area, area 2, and the full area splits up into two smaller areas. So that is what this property of the definite integral is saying. And it's pretty clear what happens when the function is greater than 0. Let's dig in a little bit more to the signed area problem and discuss what happens. Does this same property of the integral happen? Does this property work if the function is sometimes less than 0 and sometimes greater than 0? Do we get the same property? Okay, so let's take a look at another example. Okay, here is a great one that is given. Okay, let's look at the function 3x squared minus 3. Okay, we should see a graph just a moment that looks just like the blue region there. Okay, so we've got the interval from 0 to 3. We've got the black dotted line function is the original function, 3x squared minus 3. And we can see right here that this function, 3x squared minus 3, is equal to 0 when x is equal to positive 1. So right here, this function crosses the x-axis at that point. Okay, so naturally this blue region is split into two pieces. A part where the function right here, the function is less than 0, and another part where the function is greater than 0. Okay, so let's look and see what happens if we try to do the definite integral from 0 to 3 of this function. You could do the fundamental theorem of calculus on that. Pretty easy to find the antiderivative at 3 minus the antiderivative at 0. Okay, the antiderivative of this function is x cubed minus 3x. Pretty easy to plug in the values for this function, and you will find that once you do that, you get a definite integral that has a value of 18. Okay, so 18 is the definite integral from 0 to 3. So the black region here, this definite integral from 0 to 3 of this function is 18, a positive 18. That meant that there is a total signed area of 18. Okay, but we know that this region has a part above the axis and a part below the axis, so there is a positive and a negative area. Okay, so if we look at the definite integral from 0 to 1 of f of x dx, this should have a negative signed area. So the answer is going to be negative some number. We need to figure out what that number is. Okay, so if we back this up and go from 0 to 1 and find the area or the signed area from 0 to 1, okay, again using the fundamental theorem of calculus, you will get a negative 2 for your answer. So this area right here has a signed area of negative 2. Okay. But then there is the blue integral here, which is the definite integral from 1 to 3 of this function. Okay. Fundamental theorem of calculus again, f of 3 minus f of 1 will give you a value of, let's figure it out. So we want to go from 1 up to 3. Okay. And you get a value of 20. Okay. So what we're seeing in this problem, if we add a page below, right? That the definite integral from 0 to 3 of f of x dx came out to be a value of 18. That was the total signed area. It meant that there was a definite integral from 0 to 1, and then an integral from 1 to 3, and the blue integral had a value of 20. There was an area of 20, and it's an area, positive signed area. And then the other value had a value of -2, so we had a negative area, an area below the axis of signed area equal to -2. And together, -2 plus 20 turned out to be the value of a net positive area of 18. So this is the important thing to remember, that definite integrals don't necessarily give you area. They give you total signed area. They take into account the pluses and minuses of the area. So this area, the large region was 20. It was a larger area, but then the definite integral subtracted the area below the axis. And that's why our net area is equal to 18. Okay? So again, here we're using the main property, the property of the integral. And it's important to have this property because it helps us deal with the positive and negative area problem.